The vitreous humor, a transparent gelatinous fluid that fills most of the eyeball, has an index refraction of 1.34, similar to water. Not that it's similar to water, but the index refraction of water is about 1.33. Visible light ranges in wavelength of 400 nanometers to 700 nanometers, as measured in air, which is assumed to be similar to space or vacuum. The light travels through the vitreous humor, strikes the rods and cones and the surface of the retina. What are the ranges of wavelength of the light as it approaches the retina within the vitreous humor? Express your answer in nanometers separated by a comma. Okay, so concept here, we're going to say that the vitreous humor is kind of like this. Hope we have a blob, and inside we have vitreous humor, which I'm going to say is blue. I assume it's actually transparent. And we have a photon, wavelength of light, that comes and passes through it. And so the idea here is the speed of light and wavelength will change when it changes medium. I don't know if the speed of light actually changes. My understanding is that the theory goes along the lines that light is absorbed and then re-emitted, and the delay in that creates an apparent slowing of the light. Doesn't matter. As far as we're concerned, light slows down in any medium other than vacuum, which in fact is no medium at all. So on the outside we have velocity equals speed of light. Wavelength is either 400 or 700 nanometers. And then the frequency we can find. So let's see. 400, 700 nanometers. Yep. Equals, and I'm going to say equals question mark. And then I'm going to call this outside, and I'll call this 1, this area 1, and then inside the vitreous humor, I'm going to call area 2, just for convenience. And so for starters, what I'm going to do is I'm going to find frequency. So velocity equals distance divided by time. This is my mnemonic. For C equals wavelength times frequency. Therefore, frequency at 400 nanometers is going to be equal to speed of light over wavelength, which is going to be 3 times 10 to the 8th, more or less, divided by 400 times 10 to the negative 9th. Yep, I'm good with that. Which is equal to 3 divided by 400 times 10 to the 17th. And I just moved the 10 to the negative 9th up top. When you go from if you convert a base and an exponent from numerator to denominator, you basically just switch the sign. So this becomes 10 to the 8th times 10 to the 9th, which is 17. All right, game face. 3 on, clear. 3 divided by 400, and we're going to multiply this by 10 to the 17th. 10 to the 17th. And that should give us a number, 7.5 times 10 to the 14th, which is 7.5 times 10 to the 14th, and that's going to be hertz. All right, so then we're going to do the same thing, but we're going to do the frequency of the 700 nanometer. I'm going to call that F700. And that's going to give us 3 over 700 times 10 to the 17th. There's probably some clever math thing I can do to just kind of find that. I could. And multiply that by 7/4. That's okay, I'm not going to do that. 3 divided by 700 times 10 to the 17th. And that gives us a frequency of 4.3. Yep, 4.3 times 10 to the 14th equals 4.3 times 10 to the 14th hertz. All right, and so the reason I did this was the wavelength and the speed of light will change when it goes into a new medium. So this will be V2 wavelength 2, but frequency, write it down here, frequency stays the same in the new medium. And so now that we know the frequency, we can use the new speed of light, because if we're given the index of refraction is how much slower it moves in the new medium. So velocity 2 equals speed of light divided by the index of refraction 2, which they gave us is 1.34. So going back to our equation of C equals wavelength times frequency, to find the wavelength, we're going to do C divided by frequency. Yep. So lambda 400 in medium 2, and the 400 just means 400 nanometers. It was given to us as 400 nanometers. It's going to be not actually 400 nanometers. So the C, that's not actually C. That is the speed of light in this new medium, which I'm going to call V2. Oh, there we go. V2, which in vacuum is C, in this case, not C. So this speed, V2, is going to be 3 times 10 to the 8th divided by 1.34 divided by the frequency, which is 4. Let's see, first one we had was 7.5 times 10 to the 14th. I'm going to put that in the calculator real quick, and I could probably simplify that, but I'm not going to. 3 times 10 to the 8th divided by 1.34 divided by, I'm going to do quantity here, 7.5 times 10 to the 14th. That gives us a value of 2.99 times 10 to the negative 7th. 2.99 times 10 to the negative 7th, which is the same as 299 nanometers. So what happened was we started with 400 nanometers and on the outside, and then when it entered the, what was the name of this? Something vitreous humor. The wavelength became shorter, and it became shorter by the index of refraction 1.34. So if we did 400 divided by 1.34, that would give us the 299. That's a completely legitimate way to do it. That's probably how they expect us to do it. I like to solve for frequency then and kind of do that extra step in there, because it makes more sense to me. Like, all right, the speed changes, the wavelength changes, but the frequency is going to stay the same no matter what medium. So the first answer here, I'm going to round this up to 300 just to be, no, I'll do 299. 299 nanometers for the first one. And then for the next one, I'm just going to skip the steps here. 700 divided by 1.34, 522. 522 nanometer. I could have gone through the exact same process right down here. So the wavelength of the 700 nanometer photon in medium 2 would be 3 times 10 to the 8th over a 1.34 divided by our frequency, which we know is 4.3 times 10 to the 14th. And if I did that math, I'd get 522 nanometers. So that's the concept. Frequency stays the same. All right. What are the ranges of frequencies of the light as it approaches the retina within the vitreous humor? So this is, what is the frequency on the outside before it enters the vitreous humor? That question doesn't really matter because it's the same inside and outside the vitreous humor because it stays constant. We already have that answer. We have 4.3 times 10 to the 14th is the min. And no. We have, yes, that is the min. 4.3 times 10 to the 14th is the minimum right here. And the maximum is going to be 7.5 times 10 to the 14th. And those will both be in hertz. Already solved for those, so it makes life easier. What is the speed of light as it approaches the retina within the vitreous humor? So this one is, what is the speed of light on the what is the speed of light just as it approaches the retina? Oh, within the vitreous humor. So this is the speed of light within. So this is saying solve for V2. That's going to be this value and that value. The speed of light, I'm going to call V2. The speed of light in medium 2 is going to be speed of light divided by the index of refraction of medium 2. And that's why space or air is assumed. It had to have an index of refraction of 1, because what you're doing is you're basically dividing speed of light by 1, which is just the speed of light. So long story short for this one, I'm going to do 3 times 10 to the 8th divided by 1.34, and that gives us 2.24. So that's going to be 2.24, that's terrible handwriting, 2.24 times 10 to the 8th meters per second. And then they don't ask us for each light, the speed of light for both of those in medium 2, the vitreous humor, is going to be the same. So there's not a min or max. The min is 2.24 times 10 to the 8th, and the max is 2.24 times 10 to the 8th, because they are the same. So that's the idea with this one. I hope it helped to kind of recap what happened here. They're basically talking about the entire concept here is when light enters a medium that's not space, vacuum, the speed of light is going to change and the wavelength is going to change, but the frequency stays the same. And the speed of light is going to change by a factor of, you divide the speed of light in a vacuum by the index of refraction. Speed of light can only slow down, cannot go faster. Speed of light is a maximum speed, so nothing can make it go faster than the speed of light. And then with the wavelength is going to shorten by the index of refraction as well. I don't like to think of it like that. I like to think of it as frequency stays constant, solve for the frequency, transfer the same frequency over to the second medium, and then solve again for the wavelength. So it just helps keep things cleaner, fewer mistakes, but the math turns out to be the same. So I hope that helped. See you next time.